Evening, I'm Spot on Weather meteorologist Matthew Euler. Welcome to my latest video here on the Spot on Weather YouTube channel. Tonight I'm going to discuss the MJO, the Madden-Julian Oscillation in La Nina winters. As you can see here on the title slide, I'm going to really go in depth. I'll tell you about the overview here in a few moments. But as you can see here on the title slide, I'm showing a couple of graphics here. The first graphic here on the left is an actual example of the MJO and how these different lines represent how the MJO changes and kind of goes in and out of these various MJO phases. I will break this diagram down here shortly when we talk about MJO. Over here on the right, this is showing you La Nina type conditions. You see the bluer shading here. That blue shading indicates water temperatures running below normal across the equatorial, central Pacific, and eastern Pacific as well. So we are going to examine how has the Madden-Julian oscillation, MJO, behaved in previous La Nina winters. So the overview of tonight's presentation, we're going to look at a review of La Nina winters first. Then I'll talk some more about the Madden-Julian oscillation, MJO, defined, kind of describe what it is and why it's so very important, including its impacts globally. And then I'll talk about the MJO during La Nina winter specifically. What did those MJO phase diagrams look like in the La Nina winters? And then I'll go ahead and share my final thoughts to close out tonight's presentation. Over here on the right, I'm showing just an example of how the jet stream can vary in its wavelengths, and you can get these troughs and these ridges, and you have this hemispheric circulation, this long wave pattern. And I talked a lot about long waves in my summer training series on long waves. So if you want to really know more about these features, these long wave troughs, these long wave ridges, please feel free to go back and look at my training series from the previous this past summer. But the MJO helps to shape how this long wave pattern actually ends up downstream from the MJO. When we talk about the past La Nina winters, I'm going to stick to the same theme in tonight's presentation, okay? I'm going to stick to the La Nina winters going back to 2010. We're going to go back to those La Nina winters back to 2010, all right? So I will focus in solely on those winters. I'm not going to go further back in time than 2010 because I just kind of wanted to get a quick little sample size to see how the MJO changed amongst these winters. We do have, some sample size to work with here, even going back to that winter of 2010-2011. So what exactly is the Madden-Julian oscillation, the MJO? Let's define it. The MJO is a mode of subseasonal atmospheric variability that influences the location and strength of tropical precipitation. It typically starts in the Indian Ocean, and it really moves from a west to east direction. It moves west to east across the tropical waters, from the Indian Ocean right on into the maritime continent of Australia, that area, and then working its way eastward towards the western Pacific. Now, it consists of large-scale tropical atmospheric convective cell. Of a large-scale tropical atmospheric convective cell is characterized by an area of deep convection, flanked on both sides by subsiding or sinking air, which is dry and clear. The MJO produces persistent 1 to 3 week changes in the atmospheric flow and the propagation of synoptic scale weather systems. Now, this type of change the MJO produces kind of gets back to my overview here, this graphic showing the various long waves in the northern hemisphere. This configuration and how these long waves line up, whether it's a trough or ridge, really matters to our weather that we experience here at the Earth's surface. So the MJO can play into whether we have a more meridional north-south jet stream or whether we have a more west to east highly zonal jet stream. It also impacts where storms develop downstream in the wintertime. And I'll show you some examples of that here shortly. Bottom line here is during one MJO stage, the Pacific Ocean storms tend to be stronger and farther south in their storm track when they come into the U.S. West Coast. And I'm going to show you examples again of some of these downstream effects into the U.S. during the winter season. All right, so when we look at the MJO over here on the left, this is courtesy of NOAA. This is an example of the MJO, which is going to be characterized by this really deep color green upward directed motion here, upward pointed arrow here. This indicates your MJO itself. Whenever the air rises more vigorously in the tropics, it usually results in convection, some showers and thunderstorms. And beneath this cloud, this growing tall cloud, you get a lot of stormy and wet conditions. In this case, we're showing the MJO across the Indian Ocean. This is generally where it's going to start. And then over time, it's going to slowly drift to the east. It's going to work its way from west to east. Initially, it's going to work its way across the maritime continent of Australia, which is represented by the red X here, and it's going to eventually then work its way even further east into the western tropical Pacific area. Now notice with the MJO, it's associated with upward vertical motion, rising air by this green arrow. At the top of this strongly rising air motion, though, we have that upper level divergence. Okay, so notice how these air streams kind of spread apart up at 200 millibars or 40,000 feet above this upward vertical motion, okay? And that is going to alter the weather pattern downstream into the Pacific, into the west coast of the United States, can even result in jet stream configurations that favor colder temperatures in the eastern U.S., as far away as eastern U.S. Notice on both sides of this MJO, this upward directed motion here, we have sinking air motion. So we have clear skies whenever the air sinks vertically. So on both sides of the MJO, you have sinking air motion. Now over here on the right, I'm showing you the MJO phase regions, and they range from 1 to 8. So let's say the MJO is in phases 4 and 5. I'm just going to circle it right here. Let's say the MJO is in phase 4 and 5. That means your convection is going to be favored, your increased clouds and precip is going to be favored right around the maritime continent of Australia. What happens if the MJO goes to phase 8? That means my rising air motion, my greatest enhanced vertical air motion, rising air, clouds and precipitation are going to be right around the international dateline to the southwest of the Hawaiian Islands. So the MJO may start in phase 2 and 3, then work its way towards 4 and 5, and then eventually work its way toward the western Pacific, 6 and 7, or even 8. Now, what does the MJO do as far as impacts? Within the tropics themselves, it results in changes in the distribution of clouds, rainfall, and the wind. In the tropics, the MJO can also modulate or change monsoonal rains. It can change both the timing, the onset of these monsoons, the strength and intensity of these monsoons can be impacted by the MJO. This also, in the tropics, MJO will enhance your tropical cyclone development in specific phases. Now, in the subtropics and the middle latitudes, the MJO is going to help determine the position and strength of jet streams. It's also going to modify U.S. winter weather, and we're going to see higher risks of heavy rain, something known as atmospheric rivers into the west coast of the United States, and also can result with the right jet stream configuration, the right MJO phase. It can result in colder temperatures across the eastern U.S. Here's a couple examples now of the different phases of the MJO. So we have MJO phase 2 diagram, the impacts globally here on the left. MJO phase 6 is on the right. What I'm trying to show you is how the cloudy skies and the clear skies change over time. So when we have MJO phase 2, look at the diagram here on the left, we have enhanced rainfall and enhanced cloudiness across the Indian Ocean. All right, I'm going to draw this out, okay? So MJO phase 2, let me get my pen back out. I want to show you something really cool. So whenever you see green colors, I want you to think of cloudier skies in each of these charts or diagrams. Green means cloudier skies and most likely enhanced precipitation. Where you see the brown coloring, that's indicative of clear skies. Now, that really ties in with outgoing long wave radiation. It's abbreviated OLR, outgoing long wave radiation. The OLR is typically going to be highest when you do not have any clouds. So under clear conditions, your OLR values are going to be higher. And then in these green areas here, that means you have a lot of clouds. So your outgoing long wave radiation is going to be a lower value. Now I want to show you this though. Now look at this graphic here, again here on the left. This is MJO phase 2. Where the green areas are, again, increased clouds, more cloudy, and also rising air motion and most likely precipitation. So wherever you see green, I want you to imagine that the air is rising vertically. Okay? I'm just going to draw up arrows to indicate upward vertical motion of the air. Wherever you see the brown, I want you to associate that with downward sinking air motion in the vertical. Okay? All right, so that's what I'm saying. MJO phase 2, this diagram on the left, is showing you upward vertical motion, enhanced cloudiness, and precip in the Indian Ocean. It shows sinking air motion and drier weather, clearer skies, in the brown shading here across the western portions of the western Pacific. Now, look at the storm track when we go MJO phase 2. Let's pay attention to mid-latitudes now. So we have an enhanced storm track with the jet stream pretty much running west to east. It's basically indicated by this purple arrow. So we got a strong west to east jet stream in MJO phase 2, working its way west to east. And we also have increased atmospheric river activity along the U.S. West Coast. Way wetter than normal along the U.S. West Coast when the MJO is in phase 2. So can you believe that rising air motion and enhanced heavy rain in the Indian Ocean actually favors increased atmospheric river or flooding events along the U.S. West Coast? I mean, look at this connection. I'm going to draw just a red dashed line all the way from the Indian Ocean. My dashed line is the connection here all the way to the U.S. West Coast. Just impressive. We're enhancing the storm track, the jet stream, the winds within it are stronger. They're more west to east, transporting a lot of moisture into the U.S. West Coast. Interesting, right? Now, on the right, I'm showing MJO phase 6. Look how things change here. Again, I'm going to draw these up and down arrows to indicate, up arrows indicate increased clouds and precip, down arrows indicate less clouds, clear skies, and less precip. So what happens at MJO phase 6 now? Well, the area that was wet and cloudier in phase 2 in the Indian Ocean is now drier than normal. And now look at where the enhanced rising air motion is located during MJO phase 6. It's just to the east of the maritime continent, across the western equatorial areas there, the tropical western Pacific. All right, so do you notice here at MJO phase 6, again, where you have the MJO, which is going to be this area right here. MJO is going to be this enhanced rising air motion. This is a convective or enhanced rainfall phase, the MJO here. And on either side of that upward vertical motion, I'm going to draw the upper level divergence over the top of this. Okay. You have sinking air motion, and then the air is going to converge at low levels like this. So the atmosphere is a three-dimensional model, okay? It's three-dimensional, where the air rises, eventually at the top it's going to diverge or spread apart, and then you see the sinking air on either side of the MJO in this case. Now, this was a really cool diagram. I was looking at the ENSO blog. This is courtesy of NOAA, the ENSO blog they do. It's just excellent. This was a great analogy. I wanted to make this easier for you to understand, okay? So we have this cruise ship here. It's called the SSS ENSO. The SS ENSO, okay? Here it is, SS ENSO. And then you have this small little speedboat called the MJO, all right? Both of these vessels are making their way through the water, right? The cruise ship is representing the more stationary El Nino Southern Oscillation, and ENSO could be La Nina or El Nino in this case. So this is your basically cruise ship stationary ENSO pattern, creates these rolling waves. The speedboat represents the rapidly moving Madden Julian oscillation MJO traveling through the waves created by this bigger vessel, the SS ENSO, and that alters the wake of the the wake the MJO speedboat is producing. Now this floating person over here in the diagram is going to represent the United States. And the U.S. over here, this person is going to feel those waves from both the El Nino Southern Oscillation ENSO as well as the MJO. All right, and that's what the U.S. feels downstream from these impacts. I thought this was a cool diagram, and you see the atmospheric impacts wording is written here. But there's waves created from both the El Nino Southern Oscillation, there's atmospheric waves, similar to waves in the water, and there's smaller waves behind the speedboat, the MJO. And so sometimes these waves can act with each other, sometimes these waves can act against each other. But regardless, you're probably going to have some sort of atmospheric impacts downstream across the United States during the winter. There it is. This is courtesy of climate.gov. This cartoon was actually done by Emily Greenhall. So excellent representation here. Now, speaking of combining MJO and La Nina, we're going to examine this relationship a little bit more on this slide. So we have on the far left, okay, we have just the MJO impacts here on the far left, these two pictures. In the middle two pictures, we have the impacts of La Nina during the winter across the U.S. And then on the far right, we have the combined impacts of both the La Nina and the MJO. So let's take a look. We're focused on this boxed area in each of these maps. You see this dark boxed area here across Florida and the Gulf Coast. All right, so if we look at just MJO alone here in the upper left, where I got my red dot here, this is the general results of MJO being in phases 6 and 7 in the winter. And you notice how the brown coloring here, the yellow and brown coloring indicates drier than normal conditions. So we're looking at precip anomalies here on all of these maps. So green means above normal precip, brown means below normal. So MJO in phases 6 and 7 in the upper left here is generally going to result in drier than normal conditions across the Gulf Coast, Louisiana, Mississippi, Alabama, Georgia. Also drier than normal from Virginia right up the I-95 corridor, right up to the big cities of the Northeast. Now, if we have MJO phases 8 and 1 down here in the bottom left, notice how those drier than normal areas now become wetter than normal from the Gulf Coast, Louisiana, Mississippi, Alabama, Georgia, right on up from the mid-Atlantic coastal areas up through New England, all the way up. So that's MJO phases 8 and 1. So look at the difference during winter. MJO phases 6 and 7 drier than normal in this boxed area. MJO phases 8 and 1 is a different story. Now what happens if we just look at La Nina here in the center? These two graphics. All right, so we have during La Nina winters, typically what do we have? We have drier than normal conditions across the Gulf Coast states. We have drier than normal conditions across the southeastern U.S., extending up into the southern mid-Atlantic. This is very much normal for La Nina winters. Okay? Now what happens if we take MJO and we add the effects of MJO in phases 6 and 7 to the La Nina? We combine the effects. What happens? We get a much drier results over here in the upper right graphic, right here, combined. MJO phases 6 and 7 plus La Nina results in very dry conditions in the boxed area here along the Gulf Coast. Also results in very dry conditions all the way up from the mid-Atlantic, Pennsylvania, up to New England. So we have a stronger signal in this case when we combine MJO and La Nina. Stronger signal for the boxed area. This is known as constructive interference. Constructive interference refers to amplification of both the MJO and the La Nina. we get back to this slide here, we're saying that the wave action associated with the ENSO, in this case La Nina, is in phase with the waves created by the smaller speedboat, the MJO. That results in a much greater probability of specific conditions, in this case drier than normal. What happens here in the bottom row though? We get a MJO in phases 8 and 1, which is indicative of wetter than normal conditions along the Gulf Coast in this boxed area. And then we add La Nina into the picture. Well, La Nina generally favors drier than normal conditions for the Gulf Coast. We add these two up, wetter than normal with MJO phase 8 and 1, drier than normal expected with La Nina conditions, and guess what? You're still getting wetter than normal conditions because this MJO is overpowering the effects of La Nina in this case. MJO is phases 8 and 1, perhaps it's in stronger phases. 8 and 1 is going to overpower the drier than normal typical weather you'd get with La Nina in the winter in this boxed area, and now it's actually wetter than normal. So a weaker signal or an opposite effect, when you have MJO and La Nina working against each other, this is known as destructive interference or wave cancellation. Okay? Hopefully you understand that. This is a very important concept to grasp. And this is what makes winter forecasting so very challenging, because you may have one of the teleconnections, such as MJO, indicating one thing in a specific MJO phase, but then you have the effects of ENSO. Do they cancel each other out, the effects? Do they amplify the effects working with each other? Is one stronger than the other? I mean, there's a lot of variables here when we talk about climate drivers. Now let's examine the past La Nina winters going back to the 2010-11 winter season. We're going to first examine the strong La Nina of the 2010-11 winter and look at the MJO. Before we do that, I want to just briefly explain how to interpret this MJO phase diagram. The MJO phases run from phase 1 all the way through phase 8. And each of these colored lines represents a specific month. In this case on the left, and really for any of these cases I'm going to show you, going back to the La Nina winters, to the 2010-2011 season, the blue line represents December, the month of December. The green line represents the month of November, and the red line on this left-hand graphic on each of the following slides, red is October. So red indicates October, green represents November, and blue is December. On the graphic here on the right, the MJO phase diagram on the right, we're going to be looking at January through March on each of the coming slides that you're going to see. And blue, let's start with red. The red line indicates January. The green line represents February, and the blue line represents March, the month of March. Now you'll see these little numbers along each of these colored lines, right? And that represents the specific day of the month these various phases occurred. All right, so MJO diagram, phase diagram, you generally go from phase 1 all the way through phase 8. That's indicated by these numberings here, these numbers. Whenever you have the MJO and enhanced convection in the Western Hemisphere in Africa, you're in MJO phases 8 and 1. Whenever the MJO and the enhanced convections in the Indian Ocean, we call that MJO phases 2 and 3. Whenever the enhanced convection and MJO are in the maritime continent area around Australia, we call that phases 4 and 5. And whenever the MJO and enhanced cloudiness and precip are out in the Western Pacific, which generally correlates to MJO in phases 6 or 7. Now, the farther out you get from the center small circle here, you notice I have a small little inner circle at the center of the diagram. Whenever the lines are within the small inner circle, that basically means the MJO is very much negligible. It's not having much of an impact on the weather. However, the farther out and away from the middle of the diagram the lines get, the further away they are from the center point, that indicates a stronger magnitude MJO and much greater impacts. Okay, so now that I've said all that, let's examine some of these MJO phase diagrams from past La Nina winters. Again, starting with 2010-2011, we had a strong La Nina, and you notice the MJO was a little bit stronger into phases 4 and 5 and wrapped around to 6 in the month of October of 2010. But the months of November and December were fairly close to this small inner circle, so MJO was not as strong in those months in November and December 2010. Over here on the right, the MJO became very active in the month of January 2011. Notice how this red line is getting further away from the center point of the phase diagram. That indicates a more active MJO phase. So the whole month of January, by the 17th, it's sitting right here in the Western Pacific, right on the border of phases 6 and 7. Then it gets a little bit more amplified and stronger. The 19th, right on through the 23rd of January, and then it rotates into phase 8. 24th, 25th, 26th, 27th of January of 2011, before rotating back into that small inner circle. I'm trying to think, there was something else I wanted to mention here, but it escapes my mind at the present time. But just keep in mind that, again, the stronger this gets... Oh, I know what I want to mention. Okay, let me draw this out for you before we continue. All right, so for the U.S., the eastern U.S., let's put it that way, phases 8, 1, and even 2, these are the cold phases of the MJO. So if you see the lines in 8, 1, and 2, any of these lines from any of the previous months of previous winters, that means we're in a colder phase for the eastern U.S. However, if we go to 3, 4, and 5, like over here on this side of the MJO phase diagram, that is indicative of warmer or milder temps in the eastern U.S. I just wanted to mention that. So you have a cold phase of the MJO diagram, a cold side of it, and a warm side. That's what I wanted to mention. All right, moving on now to the moderate La Nina of 2011-2012, that winter season. Look over here in the diagram on the left. Excuse me. Notice this diagram on the left. October was once again very busy, where the MJO was rotating into phases 8 and 1. And then it became active in November and December as well. Remember, this green line is November, so late November, right into early December, it went into more active or stronger phases 3 and 4. Over here on the right, we see it was very active in February, which is the red line. I'm sorry, no. February is the green line, so notice how in February, how it got stronger. MJO got stronger in phase 7, then it rotated into phase 8, which is going to be a colder phase in February for the eastern U.S., and then it rotated into phase 1, then phase 2. The blue line is March, so it stayed very active. Look at the blue line, how far away from the small inner circle it is, into phase 3 in early March, and then it just rotated right up, stronger phase 4, 5, 6, and wrapped around again. So this was a very active MJO in the moderate La Nina winter of 2011-2012, specifically in February and March. If you look at the weak La Nina winter of 2016-17, notice the green line here, that's November. In the months of October and December, the red and blue line is kind of sitting in here in the middle of the diagram, so it's not a very strong signal from the MJO. But it did get active in November, coming out here in phase 5, 6, 7, and then rotating into 8 here from the 12th to the 15th of November, and then wrapping around to phase 1 and phase 2. Over here on the right, we see the MJO is more active, especially in February. Look at how far, this line in February, mid-February of 2017 is almost to the edge of this MJO phase diagram into phase 8. So this is a very strong signal for the MJO in February of 2017. Looking at the weak La Nina winter of 2017-18, notice in October it was very strong. Look how far from the center of the diagram it gets out into phases 5 and 6 and 7. And then the blue line is December, so it did come back out in December. Pretty quiet in the month of November, the green line in the center of the diagram, but then into phases 5, 6, 7, and weekly into phase 8 before coming out and getting stronger by the end of December in MJO phase 2. Over here on the right, this would be January through March 2018. The MJO was very active in January and February. Remember that the, red line is January, so look at, it's on the warm side of the MJO phase diagram, though, this red line, right? It's in 3, 4, 5, 6. This would be a milder temperature regime for the eastern U.S. in this case. And then the green line indicates February, and it got stronger into phase 7 before getting weaker into phase 8, phase 1. And then let's examine the temperatures. I decided to throw these temp anomalies just to kind of show you the impacts potentially of the MJO. All right, so this is in a weak La Nina winter of 1718. Again, remember it was stronger in the warm phases in January, and then it went into some colder phases, 8 and 1, and even into 2 middle to late February. So let's examine this. This was February 2018 temp anomalies. These temp anomalies occurred after the MJO was strongly in the milder phases 5 and 6 out here. Okay, this red line here. This is January. So after the MJO went up into phases 5 and 6, got really strong from the 22nd of January right on through the 31st of January, this was what followed across the east. Look how above normal temperatures are from Maine all the way down to Florida. I mean, this is really interesting, isn't it? If we look at March and April of 2018 now, March 18 is on the left and April of 2018 is on the right. So what happened as we got into February? It went into the colder side of the MJO phase diagram at phases 8 and 1. And what happened in March? What happened in March after this went in the colder phases in late February? Well, we got this instead. We got colder than normal temperatures across the mid-Atlantic, blue and green colors. Purple is even exceptionally below normal temperatures. But you see what happened here, how the temperature anomaly configuration changed just after examining the MJO plot for this winter. If we look at the moderate La Nina winter of 2021, it was very active in the month of October here on the left, the red line on this diagram on the left. It wasn't very strong in December, the blue line. It tried coming out of the into phases 2 and 3 weekly into phases 2 and 3 with convection across the Indian Ocean in mid-November through the third week of November. But October was the strongest signal in this case. Over here on the right, January 21 to March 2021, not as active. I mean, February, this green line got a little bit more active across the Western Pacific with the MJO, but then it kind of worked its way back in towards the center. March was closer to the inner small circle here, January as well. So this wasn't a this wasn't a very active moderate La Nina MJO situation in 2021. What about the moderate La Nina of 21-22? October through December is on the left here, showing the MJO got a little bit stronger, this blue line in the month of December of 2021, going into phase 6 and phase 7, convection, enhanced rainfall across the tropical Western Pacific. And then over here on the right, the months of January 2022 to March of 2022, we did see some changes in the MJO these months. We'll see the red line is January, so it was mainly towards the center, very inactive until about mid-January. Then it kind of worked its way out into phases 7 and 8. And then in the blue line here, again, it's indicative of March, kind of worked its way out into phases 2 and 3, a little bit stronger in March, as well as February, kind of worked into phase 3. So the convection this particular period, January 22 to March 22, was really focused on the Indian Ocean. And then the weak La Nina winter of 22-23, what the MJO looked like, here are all the lines, the 3 different months. October red, and then you have green line is November, and then the blue line is December. Not really expanding very far out from the center of the MJO phase diagram. So fairly weak, but the convection was focused across the Western Pacific and MJO phases 6 and 7 on this side of the MJO phase diagram. Over here on the right, now this got interesting. This was a pretty mild winter overall. And then you had the MJO really go off, get very active in March, got very strong. Look at this blue line, that's March. Notice how it basically rotates counterclockwise from phase 7 into phase 8. And it's off the chart to the left of the number 8, the phase 8 here. This is how strong this thing was. So it went into colder phases in March in 8 and 1. So here are my final thoughts on tonight's presentation. Okay, first bullet point here is important to consider. I was showing you the ENSO, the bigger ship, and then the motorboat, the MJO. The MJO and La Nina can act out of phase. In this case, we call that destructive interference, or it can act in phase. These two components can act together or against each other. When they act against each other, it results in a canceling out effect overall when they act against each other. And that's called destructive interference when the waves are out of phase. It can act together in phase, the waves, both the MJO and the ENSO or La Nina in this case, resulting in constructive interference during the U.S. winter season. So look at this up here, right here. This is an example of an in-phase situation. All right, so see how, let me go ahead and draw this out for you so you understand it better. So you see how the wave of this, the trough of that is the same as the trough of that. The ridge of this wave is the same as the ridge placement of this wave. The trough of this wave at the top is the same placement as the trough at the bottom. All right, so this is a result, this basically is constructive interference when the waves are acting in unison like this with each other. So you see the ridging, the sawtooth line, both of these waves are in unison together. The troughing all the way down here, in unison. Ridging, in unison. The placement of the ridges and troughs of these two waves is exactly the same spot. And that's going to result in wave amplification or an in-phase relationship. And you know, you can call this top wave La Nina. Okay? Let's say we have La Nina at the top of both of these diagrams, and at the bottom we have MJO. Okay? So looking at the waves, how do they look in relation to each other? Are they in phase or out of phase? I'll do the same here on the upper right. This is a case of destructive interference where the waves are out of phase. So for example here, notice we have a trough with this wave, top wave. And again, let's call that La Nina. This is La Nina up here at the top. And then this is going to be MJO at this bottom portion here, upper right hand example. But we have a trough, let's say we have a wave trough and then a wave ridge, which are going to cross cancel each other. We have a wave ridge here with the La Nina, but then we have a wave trough with the MJO, and so on. So you get less amplification of the wave, you get destructive interference in the out of phase condition. And that's what I'm trying to get at here at this top bullet. Sometimes the MJO and La Nina can act in phase with each other, and that's going to enhance the effects that you would typically see with MJOs in specific phases and La Nina in the winter season in the U.S. The out of phase relationship again between MJO and La Nina will cancel out the effects of La Nina. You know, so you might be sitting here saying to yourself, hey, we have a weak La Nina forecasted here for the upcoming winter for the U.S. Oh, that surely means it's going to be drier and warmer than normal along the Gulf Coast, right? Surely means it. And then all of a sudden you get to a point this upcoming winter, let's say it's January, and it's wetter than normal for like a 2-week period. And you're wondering, what in the heck is going on? How could my forecast have been off? I saw it was going to be a La Nina winter. It should be drier than normal and milder than normal across the Gulf Coast states. But instead, it's cooler and wetter than normal for 2 weeks. What possibly happened? What possibly happened is you may have had an out-of-phase relationship between the MJO and the La Nina, and this may have canceled out the effects of La Nina. Okay? That's a very distinct possibility. If the MJO was very strong, and it's in phases 8 and 1 in the winter months, and it favors more unsettled conditions across the Gulf Coast and the East Coast in general, and cooler than normal conditions, you know, maybe you get a big snowstorm in the mid-Atlantic in January in a La Nina winter, and you're thinking to yourself, it's not supposed to happen. It's supposed to be below normal snowfall. It's a La Nina winter. But maybe that MJO moved into a favorable phase for a bigger snowstorm in the mid-Atlantic and temporarily offset the effects of La Nina. So the in-phase relationship between MJO and La Nina, again, will enhance the effects of La Nina. Rainfall. You know, can you believe it? I mean, rainfall in the Indian Ocean associated with an active MJO, it's often related to cooler, wetter weather in the western U.S. in a trough. When you get the convection and the MJO and in the Indian Ocean, you can actually set up troughing and weather the normal conditions across the western U.S. Something that happens as far away as the Indian Ocean, in the tropical areas of the Indian Ocean, can impact our weather in the U.S. much further away. It's just really amazing. MJO is going to be strongest in the northern hemisphere during the months from November to March. So this is usually when we're paying close attention to the MJO. November to March time period, the winter time. The MJO phases 1 and 2 tend to be associated with below average temperatures over much of the continental U.S., while phases 5 and 6 are linked to above average temperatures. So here you go. I mean, take a look at what MJO is doing. Is it in phases 1 and 2? Is it strong? Is it weak? And then compare it to MJO phases 5 and 6 in the wintertime and look at the temperature anomalies across the United States. It's completely a different story. So, all right, additionally, a mid-latitude response of the eastward shift of the enhanced rainfall due to the extension of the East Asian Pacific jet stream further out into the Pacific Ocean. That can occur with the MJO in specific phases, and that Pacific jet stream extension then often basically is very strong Pacific jet. It works its way west to east and just basically runs right into the west coast of the United States. And you get cases where you see the Pineapple Express, or you get cases where you get these atmospheric rivers which result in just lots of flooding rains, specifically across California, even up into portions of the Pacific Northwest. And this can simply be the result of the MJO being in phase 2 as an example. MJO activity tends to be most active during neutral and weak ENSO years. So when I say ENSO, I want you to think about El Nino or La Nina. It could be either or. But this is some research that was conducted. The MJO activity tends to be most active or strongest during neutral and weak ENSO years. And we have a weak La Nina that is forecast for the upcoming winter. So this will be something to keep an eye on. MJO activity tends to be least active during moderate to strong El Nino or La Nina years. Okay, so something to watch for the upcoming winter. Now, the MJO activity is highly variable during strong La Nina periods, and we are not expecting a strong La Nina this winter. The 07 to 2007 to 2008 winter, during that particular winter, the MJO was very active as an example. All right, so just because research says the MJO behaves a certain way in neutral, weak, and strong ENSO periods doesn't necessarily mean it's going to do it every winter. And then finally, the MJO can be broader, stronger, and faster during an eastern-based La Nina as compared to a central-based La Nina. What in the world are we talking about here when we talk about eastern-based La Nina versus central-based? It all has to do with the water temperatures, okay? Where do those cooler than normal water temperatures set up in relation to the equatorial, eastern, and central Pacific? I'll show you an example of that here at the end. I'll go back to the title slide and kind of show you that. Now, the predictability of MJO during La Nina winters is affected by, the QBO. Quasi-biennial oscillation. What in the world is the QBO? Well, the QBO is a reversal of winds between, or generally the winds in the stratosphere, the second layer of the atmosphere above the equatorial areas, above the tropics. And it's a well-known reversal of winds. When we have a westerly QBO, the winds are primarily from the west in the stratosphere above the equator. And when we have an easterly QBO, the stratospheric winds are from the east in the winter season, above the equatorial area. All right? And so there's changes to the QBO between westerly and easterly phases. We're heading into a westerly QBO this upcoming winter. It's very regular changes on the order of up to 28 months. The wind direction in the stratosphere switches over the equator between west and east. All right, so let's take a look at the QBO relationship to La Nina. During La Nina with eastern QBOs, the MJO is less suppressed and persists longer than during La Nina western QBO winters. We are headed for a weak La Nina this winter, according to the NOAA latest outlook, and we also are expected to see a westerly QBO. All right, so what does this mean? Well, the MJO is going to be less suppressed and it's going to persist longer. It persists longer and is less suppressed during La Nina with eastern QBS, but we don't have that. So what we'd expect then with this relationship from research is that La Nina and the western QBO, the MJO, would not be as active or persist as long. We'll see what happens. Now, the MJO does not cause El Nino or La Nina, by the way, but it can contribute to the speed of development as well as the intensity of El Nino and La Nina episodes. And then finally, this is my last slide, I promise. The MJO can offset the effects of La Nina, and it can become the primary climate driver in any winter season. At any point in the winter season, the MJO could just take over and dominate. Or the MJO can amplify the effects of La Nina, which we talked about with that wave amplification, or the constructive interference between the tropical convection associated with the MJO and the downstream long wave pattern. What do you have to look at here? Are the MJO and La Nina in phase or out of phase? And how will that impact the weather where you live? That's really the golden question. And additionally, there are other climate drivers, other noise exists out there in the atmosphere that can overpower or cancel out the effects of La Nina and MJO alone. These include the Arctic Oscillation, the AO, the NAO, which is the North Atlantic Oscillation, the PNA, the Pacific North American Pattern, PDO, the Pacific Decadal Oscillation, as well as the strength of the stratospheric polar vortex, whether it's strong or weak. All of these must be considered to get the total picture. You know, it's so easy to be narrowly focused in the winter season and only look at one particular teleconnection or climate driver and think you've got the whole thing figured out. But that's not the case, because all of these climate drivers interact intricately with each other, or they act against each other. And then you have to figure out, hey, what's the more dominant climate driver or teleconnection here in determining my sensible weather for the next 3 to 4 weeks. So bottom line is, this stuff is extremely interesting to me. I looked at a lot of different research papers when I put these bullets together for my final thoughts. And there's a lot of great research out there. I encourage everybody just to go up, just Google it. Just Google MJO and La Nina winters, and you'll come up with a lot of good research papers done. And again, it's a complex puzzle. Okay, seasonal forecasting is a complex thing, and there's a lot of variables that could play into the actual sensible weather and the results. That's all I got for now, everybody. Let me go back to that title. I decided I was going to go back to the title slide and show you the example of east base versus central base La Nina. Okay, let me show you this real quick, and then I'm going to wrap it up for the evening. This, where you have the blue coloring, indicates your below normal water temperatures, right, in a La Nina winter across the equatorial waters of the Pacific. But look at where the blue, the darkest blue, is in this example. It is going to be situated over the central portion of the equatorial Pacific. So this would be an example where this blue is further west. This is going to be an example of a central-based La Nina. Now, if the darker blue was immediately right off the coast of South America here, if the darker shade was here, that would indicate an eastern-based La Nina across the eastern Pacific based. All right, so that's what I was getting at in that last bullet there. Here, let me go back here. All right, that's what I was getting at here. You know, was it there? Wait. Nope. It was here. So during La Nina, that's not it either. I'm trying to find it again. With less suppressed and contribute to speed to it. Nope. Okay. I can't believe I can't find it. But anyway, whether it's an east-based or a central-based La Nina could mean the difference between, you know, how the long wave sets up and the sensible weather along the U.S. I can't believe, I mean, I have so many different bullets in here. Oh, right here, the first one. Good. It's right up here. Yep, there it was. The very first bullet, right there. The MJO can be broader, stronger, or faster during an eastern-based La Nina as compared to a central-based La Nina. So there you go. All right. I'm good now. That's all I got for now, everybody. I hope you enjoyed this presentation on the MJO. Just taking a look back at the winters of going back to 2010-11 and the MJO, how it behaved in relation to the different types of La Ninas we had, whether they were weak, whether they were moderate, or whether they were strong. I know I have a strong one in here too. That's the strong La Nina there, 2010, 2011. Then the moderate La Nina the following winter. Then the weak La Nina of 16, 17. Another weak one in 17, 18. And then the week, we have another moderate one, a weak one, and yeah. All right, that's all I got for now, everybody. Continue to work on some other great videos to share with you. Hopefully you enjoyed this. That's all I got for now, everybody. Until next time, take care and God bless everyone.